Okay, I'm sorry for those who already heard this story. I hope this will not be too boring, but okay, so let me start by explaining to you a bit the setup. As you may know, as you surely know, Yang-Mills theory is in 4 dimensions confined. This means that the only states, asymptotic states that are observed are color singlets. The problem is that the theory, Yang-Mills theories are weakly coupled at high energies, so we can control them with perturbation theory. But when we go to high length scales, so the theory gets strongly coupled. And this means that we cannot use any more perturbation theory to understand what happens. This is why confinement is so much a problem in theoretical physics. So it's hard because it occurs at strong coupling, at energy almost around the strong coupling scales of Yang-Mills theories. One possibility to try to investigate the problem is to put the theory in a box. This is because if we take the box, the radius of the box, the dimension of the box sufficiently small, we have that the gauge coupling cannot become too large. So what happens is that at some point, at some value 1 over L, the G squared at 1 over L, the gauge coupling stops running. And this means that if the radius is sufficiently small, we can still use perturbation theory. The problem is that if we choose a generic box, we may break some of the asymmetries of flat space. So the maximally symmetric choice that we can use to study gauge theories in a box is to put them in anti-de Sitter space. So let me explain to you why QFT in ADS in general, and in particular why QFT in ADS for Yang-Mills theories. First of all, we consider anti-de Sitter space. These are the coordinates, Poincare coordinates. L is the radius of ADS. We consider ADS in D+1 dimension, so D+1 dimensional bulk and D-dimensional boundary. In this case, the isometric group is SOD +1, 1. We are considering Euclidean ADS. And at Z equal to 0, we have a conformal boundary. The nice property of ADS is that the operators at the boundary have correlation functions which are constrained by the conformal symmetries. So at the boundary, if we consider QFT in rigid ADS, at the boundary we have operators whose correlation function are the correlation function of a CFT. The only difference with the case in which we have dynamical gravity in the bulk is that the theory at the boundary is non-local, so we don't have a stress tensor. The CFT data at the boundary depend on the boundary condition that we assign to the fields. So if we have different boundary conditions which respect the conformal symmetry, we can study different theories, as we will see for Yang-Mills theories. Okay, another nice property is that even when the radius of ADS is finite, ADS has finite volume. So phenomena which are not allowed in finite volume spaces are instead allowed in this case, like symmetry breaking and phase transitions. Okay, for asymptotically free theories, there is another nice point, is that we can combine the radius of ADS with the strong coupling scale to have some L lambda parameter, which is dimensionless. These parameters can be tuned in order to consider different regime. This was first applied for large N models in D equal to 2 by Copetti, Di Pietro, G, and Komatsu. And we want to apply the same idea to Yang-Mills theories. So we take Yang-Mills theory in rigid ADS, and we tune the value of L lambda Yang-Mills to interpolate between different regimes. In particular, as you can see, L lambda Yang-Mills is defined as follows. And so when the gauge coupling is sufficiently small, L lambda Yang-Mills is small. So again, when the radius of ADS is small, the theory is weakly coupled. When it's large, the theory is strongly coupled. So if we start from a very small radius, we can use perturbation theory and try to investigate what happens when the radius gets larger. So this is the theory. We need to impose boundary conditions. One possible boundary condition is, I don't know why it's, sorry, I don't know why it's, okay, I can. Sorry. Okay, that's it. Okay. So when we are at very small radius, we can solve equation of motion for the gauge field and find which are the possible boundary behavior which preserve ADS isometries. One possibility is that is to impose that the gauge field at the boundary asymptote to a global current. So in this case, these are Dirichlet boundary conditions. In this case, the bulk gauge symmetries becomes a global symmetry, and as I was saying, the gauge field asymptote to a global current, which has protecting dimension equal to d minus 1, so in this case equal to 2. And dynamical states corresponds to states which asymptote to this global current at the boundary, which are weakly coupled gluons, meaning that the theory in this case is deconfined. Okay, so let me stress the following point. We are at a small radius of ADS. We find that there is a state which is the current, which has protecting dimension equal to 2. And even when we turn on the gauge coupling, the dimension of the current remains equal to 2. So, but at the same point, we know that when we take the flat space limit, the theory has encounters mass gap and confinement. So we know that this state that we observe, which is light and charged at low energy, at low radius of ADS, must in some way disappear at large radius of ADS. But this is protected, so something has to occur to Dirichlet boundary condition. So it cannot exist when we take L to infinity.
Just a very, very naive question, sorry. So, like, I understand that with this Dirichlet boundary condition, we have this conserved current, and that, of course, states that are charged under this global symmetry, they are kind of gluons. But how do you know that there are such states? I mean, in principle, there could be, I know examples where you have some global current that is conserved some at the boundary, right? And you just don't have states. Like this is not mandatory.
Okay, but
it could be that this current just does not act in the space, for example, or that this this part, the part of the space that is charged under these currents is just completely decoupled.
Okay, but imagine a gluon in the bulk.
Yes.
This can go up to the boundary.
Mm-hmm.
And like this is a well-defined situation in which you have a gluon on its own and it gets to the boundary, mm-hmm. and this corresponds to a
yeah, if you have a gluon, certainly.
But, okay, but
yeah, I agree that if you have gluons, yeah. But I'm just asking if you want the converse.
Okay, but we are interested in the case in which we have Young mills in the inside with gluons, and at least at high energies, we know that gluons are there.
Okay, okay.
So we want to investigate.
Yeah, thank you. I think it's clear.
So you are in 4 dimensions, right?
Yes.
So why is the dimension of the current?
Because 4 dimension is the bulk, 3 dimension is the boundary. So you are the theory.
The boundary.
Yes, the global current is at the boundary. The dimension is 2.
I mean, in Euro QED, we need to consider. I mean, the dimensional transmutation formula you wrote down. Why is lambda UV not appearing?
Oh, I'm sorry.
I mean, because we do our argument I mean, in EuroQED calculation, we calculate beta function, and you see dimensional transmutation can happen between lambda Young-Mills over lambda UV. Why did we forget about that scale, or
What is lambda UV?
because let's see, the mass gap is proportional to exponential lambda over.
There's only one dimension full scale, right?
Which is
Yeah, it's the strong coupling scale. The other dimension, the whole point is that here we have another dimensional full parameter, which is the radius. But otherwise, the only dimensional full scale would be a lambda Young-Mills, the strong coupling scale.
no, I'm just saying that maybe there's another dimensional less parameter, which is okay.
I think the point is that here the Young-Mills coupling is actually a parameter in the theory, at least at the endpoint. Whereas in flat
Yes.
space, QCD doesn't have any free parameter, but like Young-Mills, it's UV complete, right? So you don't need a UV cutoff. You put it when you do calculations, but it's actually UV complete, so it doesn't have any parameters. Right? The only thing is the dimension full scale.
Your bulk, does it run? Does it renormalize?
Yeah, but at some point, it's we are considering the point at which we stop the running. So we start from the UV, we run, we end up in the theory where the gauge coupling is fixed and it's G squared at 1 over L. And this is, so we can express every quantity in terms of L lambda Young-Mills or in terms of the gauge coupling at this value of the energy, but it's the same.
I see. That's
the advantage compared to flat space, right?
Yeah, that's the point. Yeah. Okay, so what's the end point? We need to find a way to explain why this Dirichlet boundary condition stops to exist. And this is the question that we were trying to address with our work. Let me say, no? Okay. Let me say that there is another boundary condition, which is Neumann boundary condition, in which instead the gauge field in the bulk asymptotic to a three-dimensional gauge field in the boundary. In this case, instead, dynamical states can only be color singlets, and so the theory confines. So this is a boundary condition which is consistent with what we observe in flat space. And this is why we can take in principle, we can imagine that we can take its limit up to flat space. So we have two boundary conditions. So this was an idea coming from work by Aroni, Berkustong, and Yankelowitz of 2012. So the idea is that if we start at very small radius with non-boundary condition, in principle, we can go up to flat space. While with Dirichlet boundary condition, at some point, something has to occur. Maybe we don't actually know if there is a transition from Dirichlet boundary condition to non-boundary condition. What we want really to answer is why we know that Dirichlet boundary condition has to disappear. We want to understand why. So we have several proposals for the disappearance of this Dirichlet boundary condition. Let me start for the first, which is the most appealing. One possibility is that some singlet scalar operator, which is at the beginning irrelevant at the boundary, becomes marginal at some point. This corresponds, I will explain you in a second why, to a merging annihilation of CFTs. And this would mean that the Dirichlet boundary condition merges with another boundary condition that we will call Dirichlet star, and after this marginality is reached, disappear from the spectrum, disappear and become complex. Okay, so let me explain to you why. If there is an operator at the boundary which becomes marginal at some critical value of the bulk coupling, we can compute the beta function from this. We can compute the beta function associated to the operator at the boundary, and we find that the beta function has this expression. What does it mean? This means that since this is quadratic, this may have two zeros or two solutions, real solution, or two complex solutions, depending on the sign of C1 and C2. This means that if we perturb the theory from G critical, from the value at which we have marginality, we can do that preserving the boundary condition, the CFT at the boundary, only if the deformation is in one direction. But we know that for G less than G critical, the CFT is present, the Dirichlet CFT is present. So we want to show that at some point it disappears, but we know that for G less than G critical, it exists. So this means that for G less than G critical, another solution of this equation must exist, which we can call the Dirichlet star. But if G gets larger than G critical, the two CFT stops to exist, becoming complex.
Can you explain it again? So the picture here is that you're thinking of the boundary as a CFT that has some like marginal coupling.
Okay, you have the situation is the following. You are in the bulk, and you have you change the value of the coupling in the bulk. This changes the CFT data at the boundary.
Yeah.
So you have some operator at the boundary, which is at the beginning irrelevant. At some point, so it changes its dimension, changing the coupling in the bulk. At some point, it hits marginality. And this is the beta function associated to the deformation of the operator, which gets marginal for this critical value of G.
It's the boundary beta function.
Yes, it's the boundary beta function. We can, like, this is computing by considering the IR divergences, because as usual, IR divergences at the boundary in ADS corresponds to behave like UB divergences in a generic QFT. So we can compute the beta function here, and as it happens in also in flat space, this beta function has the following behavior. So for G less than G critical, we have a quadratic expression with two solutions. When G gets equal to G critical, the two CFTs merge, and then I don't know why it's there's something okay, but you can imagine after G, when G gets larger than G critical, the parabola goes below the x-axis, and so the two CFTs disappear. So what happens for regarding the RG flow? When G is smaller than G critical, there is an operator, an RG flow connecting D star with D. And the operator responsible for this flow is the operator O. This operator has, okay, as dimension, now this is the dimension of the operator delta O, and here is delta O star. So the dimension of the operator starting from the CFT D star. So this is irrelevant for G less than G critical from the point of view of D, and relevant from the point of view of D star, until it gets marginal when the two CFTs merge together. So what we want to know is if the operator, we don't know who this star is, so we cannot study this flow from the point of view of the star, but we know who D is. We know the operator who may reach marginality from the point of view of the CFT, and so we can compute the anomalous dimension of this operator to see if it approaches marginality or not. Okay, so this is one possible scenario: marginal annihilation of the Dirichlet boundary condition with another boundary condition. There are two other possible scenarios. First, an adjoint scalar operator becoming marginal. This means that if an adjoint operator becomes marginal, it can recombine with the divergence of the current, meaning that the current is no longer protected, and so it can get an anomalous dimension, and a large anomalous dimension, for example, and so the problem of having a light and colored state at the boundary is no longer is no longer there. And finally, the last point is the decoupling of the currents. This means that the positive coefficient Cj of the current two-point function at some point may vanish. This forces the current operator to decouple. While the charge, all the other charge operator diverges, the OP coefficient of all other charged operator diverge. So the theory gets sick and the Dirichlet boundary condition is no longer possible. And so what we try to do is to investigate these three possible scenarios by computing perturbatively the data at the boundary, in particular the candidates for the first scenario. So we are looking for the lightest singlet scalar operator at the boundary, which is trace JJ. This starts at delta equal to 4. So recall that the boundary is three-dimensional, so marginality is reached at delta equal to 3. The candidate for the adjoint scalar operator is instead the adjoint part of the product of two currents, which again start at delta equal to 4. And finally, we computed the correction to the Cj coefficient for to test the last scenario.
So I think another possibility for the current to mix with some other operator is if there exists an operator that is identically conserved. So if there is a vector operator that is identically conserved with the same quantum numbers, this can also mix with the current, and the current is not protected.
But wouldn't that be another symmetry on the boundary?
Sorry,
Yeah.
Would that be another symmetry on the boundary?
why is it?
Because you have another conservation law.
But this operator lives on the boundary, it doesn't live.
Yeah, also the currents only live on the boundary, right?
Yeah, so why would it be symmetry? Like, it's not like given an operator whose divergence is 0, it's not. It may be no states in which.
Usually
Topological
topological symmetry is called like that. You have some like field strength whose divergence is T0, and then you have a identically conserved current.
Yeah, but yeah, so
But what would that correspond to? Like the current corresponds to the gauge field who's at the boundary. So who's this vector operator?
well, I mean, the same question you can ask for OA.
Yeah, but OA is indeed OA at weak coupling at least. I don't know why this happens. Okay, it's computed by taking combination of currents.
So you're saying there is no candidate
For
because the reason I'm asking is because, for instance, in QED, there is such an identically conserved. So the current, the fermionic current of QED is not protected because there is an identically conserved.
which is
Vector operator is the divergence of F mu. The divergence of F mu is a vector operator which is identically conserved.
the problem is that I think the difference that here you just have these currents and all the operators that you can obtain combining these currents. You don't have other, like in the QED case, you have matter and you have the field strength, and then maybe you can try to have something like combine these two, but here you just have the currents and all the operators that you can form with the currents.
In that case, you have the one signal, right?
Yeah.
So
Oh, it's broken. I think that is the case where you trivialize that current. Like that is not really a current in the usual sense.
Yeah.
Like,
Yeah,
whenever you have an
still-
identically conserved current means that you gauge the symmetry.
Yeah.
So that's the former symmetry current, which is not a symmetry current.
But it's still an operator in the.
It's still an operator, but when it's not a billion, I don't think that's
Yeah, no, but yeah.
But
They
it's-
are an abstract section. Thanks.
Okay. Okay, so we computed the scaling dimension of the lightest single scalar operator, both for Dirichlet and non-boundary conditions. Why also for non-boundary conditions? Because these two scenarios are like really refer to the case of the Dirichlet boundary condition, but the first one in principle may also occur to Neumann boundary condition, and we want to see if this is the case or not. And then we computed the scaling dimension for the lightest scalar operators in any other representation for the Dirichlet boundary conditions. And finally, we computed the coefficient of the current two-point function for the Dirichlet boundary conditions. And we did that, the first computation with a BCFT argument that I will explain to you in a moment, and the second, the other two, with direct computation with the diagrams. Computing this quantity, we computed again the first point for the Dirichlet boundary condition, and we found a match. Okay, so let me explain to you the ingredients. So we to perform computation, both the first one and the others, we need bulk-to-bulk and bulk-to-boundary propagators. To do that, we use embedding coordinates by putting the ADS in a d+2 dimensional Minkowski space. It is just an hyperboloid. So this is the equation for ADS. We can express all the propagators in terms of the chordal distance u, which is expressed as following in terms of the Poincare coordinates and embedding coordinates. And by using spectral representation and applying solving equation of motion, we found the expression for bulk-to-bulk gauge propagator, both in Dirichlet and Neumann boundary condition, for a generic psi. In particular, we found a specific gauge, which is very convenient, because with this gauge, psi is equal to d over d minus 2, which is called the 3D gauge, the expression for the Dirichlet boundary condition really simplifies. As you can see, the expression for the ADS bulk-to-bulk gauge propagator in a generic gauge is very complicated. It's a very long expression of hypergeometrics. Here, instead, it's simply a rational function of the chordal distance. At the beginning, we didn't find a similar expression for Neumann boundary condition, but recently we found the expression also in this case. It's not so easy. It's not just a rational function, but it becomes much more compact, which makes computation with Venn diagrams much easier. Okay. So then we have the bulk-to-bulk propagators. We just take one of the points to the boundary, and we find the bulk-to-boundary propagators, both in Dirichlet and Neumann boundary conditions. And then we use these propagators to compute all the quantities that we need. So let me start from the first computation, so the anomalous dimension of the lightest scalar operators. This is based by a BCFT argument, which is the following. Okay, an ECFT has the traceless and the conserved stress tensor. A BCFT, so a CFT in the a theory which is a CFT in the bulk, but a theory with in a space with a boundary, has also a protected operator at the boundary, which is the displacement operator. And this operator has protected dimension equal to d+1. We can compute the two-point function between the displacement operator and the stress tensor, and by imposing the dimension is protected and equal to d+1, and that the stress tensor is traceless and conserved, we find that the only possible expression which is compatible with the ADS isometry and this information for the two-point function between the stress tensor and the displacement is the following. So everything is fixed except for a coefficient with this CTD, which depends on the theory we are considering.
Where is the CFT here? Because I thought we don't have a stress tensor on the boundary, but we have one on the board. So which one?
This is because this is a case the beginning of the story. Okay, now we are considering a BCFT, so a theory which is a CFT in the bulk. So we also have some CFT data at the boundary and some operator at the boundary, including the displacement operator. But here the stress tensor is the stress tensor in the bulk. Mm-hmm. Okay, what happens if we turn on some classically marginal deformation in the bulk? So the theory in the bulk, the theory becomes a QFT in ADS. So the theory in the bulk is a quantum field theory and no longer a CFT. This means that the stress tensor in the bulk is no longer traceless, but it gets corrected by a factor which is proportional to the beta function of the coupling of the operator that we are using to define the theory. So we can compute another consequence of turning on this deformation in the bulk is that the dimension of the displacement operator is no longer protected at the boundary. So we have some correction which depends on the coupling of the deformation we are doing in the bulk, and this means that this corrects the expression from the two-point function of the operator, which was the displacement operator which is the displacement operator when lambda is set to 0. So the two-point function is corrected as follows. So we have an additional term, and now all the both the dimension and the coefficient in front of the two-point function depends on lambda. We can take the trace and impose that the trace of the stress tensor is proportional to the beta function. And this gives that, okay, after some algebra, we can find the anomalous dimension of the operator, which is the displacement operator at lambda equal to 0.
Sorry, can I ask you just a simple question? Just to understand. So this BCFT that you have in the bulk now is no longer pure Young-Mills.
This is okay. This is general, so it doesn't depend on the theory. Okay, after that, I will explain to you how to use this argument to Young-Mills. Maybe you can ask later, because right now this is completely general. This holds for any theory, which is at the beginning BCFT, and then we perform a classical deformation.
So now you want to interpret Young-Mills as the deformation of the BCFT.
Yeah, that's the point. Let me just stress that this is a very nice result. Oh, I don't know why this is up.
Maybe you can also agree to be recorded. So that.
But I don't have this on my. Maybe it's that. I don't know because I don't have it here.
Okay.
Okay, thank you.
So I should interpret this last equation in if you want in an expansion in lambda. So
yeah, this is actually non-perturbative. It holds in general, but yeah, after that we can apply it perturbatively. And the nice thing is that since this the coupling is marginal, so this already starts at order lambda squared. To get the anomalous dimension at which would be a loop computation, we simply need to compute this at leading order. So this is the nice point. We don't have to perform a loop computation. We just need a 3-level computation with this formula. Okay, so how to apply all these arguments to our situation? Okay, so we start from a UV-CFT, which is made by NC squared minus 1 free gluons, and then we deform, in this case, we deform with the Lagrangian. So we deform with the Lagrangian, turning on the gauge coupling, and this, so here, in this case, the marginal deformation is the Lagrangian itself. So what happens is that, again, we can repeat all these arguments and find the anomalous dimension for the displacement operator. But who is the displacement operator in our case? It depends on the boundary condition that we choose. If we take it to compute them, we can use the definition for the displacement operator, but it's easier than that. We can simply take, there is just one, for both the Dirichlet and Newman boundary condition, there is just one operator which at g equal to 0 has dimension delta equal to 4, which is the dimension of the displacement operator in a 4-dimensional APS space. These are trace JJ for the Dirichlet boundary condition and trace FF, where F is the field strength of the 3-dimensional gauge field at the boundary for Newman boundary condition. So we can express we can compute COD and CTD by expressing the displacement operator in terms of the currents. The deforming operator is the Lagrangian itself. We can express it in terms of the gauge field. And then again, the stress tensor in the bulk, we can express it in terms of the gauge field in the bulk. And we simply need then to perform with contraction between the currents at the boundary and the gauge field in the bulk. So use back-to-boundary propagator to compute these two quantities, COD and CTD, replace them in this expression, which is a beta function for Yang-Mills theories. And finally, we can compute the anomalous dimension for the operators trace JJ and trace RF. Okay, so I will comment more later on this, but let me stress on the fact that the anomalous dimension that we find for trace JJ is negative. This means that it approaches marginality with the displacement operator approaches marginality with the Dirichlet boundary condition, while instead we have a different, the opposite behavior when we choose instead non-boundary condition. So the correction is instead positive. Okay, this is very nice, but unfortunately it's not sufficient to perform all the computation that we want. So at some point we also need to compute Witten diagrams with loops in a DS space. So because this argument only holds for the singlet scalar operator, which has the dimension of the displacement operator. For all other operators, we need to compute diagrams. And so what we do is we take a correlation function of operators at the boundary, and we compute the anomalous dimension by dividing the next to leading term, the logarithmic part of the next to leading term of the 2-point function by the leading order. So at the leading order, we just take boundary to boundary propagators and we perform with contractions. But for the next leading order, we need to compute diagrams, and these are the diagrams that enter in the computations because we have the product. We want to compute the 2-point function of the product of two currents. The last two diagrams doesn't give rise to anomalous dimension. Actually, the last one does not vanish, but it does not have an anomalous dimension because it's simply proportional to the anomalous dimension of the current, which is 0 because it's protected. And the first two diagrams instead were computed with the use of these integrals. And finally, so we can from these two integrals, we can extract the logarithmic part, and we get this logarithmic part. We plug them in this formula, and we find the anomalous dimension for the singlet operator. Then we have to project onto representation of color representation. So we find that the anomalous dimension for the singlet operator is this one. Then we project on all the other representations which have the same anomalous dimension, and it is that this one. This is the same computation that we did with the VCFT argument, and they match, which is nice. So that we can trust more, because this was actually this result was numerical, because we needed to perform this integral is an infinite sum of hypergeometrics, and so we cannot compute it analytically, but using our result with the VCFT argument, we can make analytical all these anomalous dimension. And so again, we find different signs. For the singlet representation, we find a negative anomalous dimension. For all other representation, we find a positive anomalous dimension. Okay, the last computation was to compute the correction to the current 2-point function, the coefficient of the current 2-point function. In this case, so these are the diagrams that we computed. We computed the 2-point function of two currents at next to leading order. These are divergent. So we need to add also a counter term to remove divergences. And we find, okay, this diagram vanishes in our nice gauge. We find this value for the correction of the normalization of the 2-point function. Okay, so these are all the results that we got. Let me comment a bit. Okay, so we found that the lightest singlet scalar operator has negative correction. Recall that our first scenario was marginality of the singlet scalar operator, and this is reached, since this is negative, this is reached when delta is equal to 3, which corresponds to a value of L lambda Young-Mills equal to 0.37. We also computed the anomalous dimension of the product of two currents in any other representation, in particular the adjoint, and we found a positive anomalous dimension. This means that the Higgsing scenario in which the adjoint operator recombines with the current is disfavored because the anomalous dimension is positive, so it gets farther from delta equal to 3. And finally, we computed the correction to the current 2-pi function, and we found a negative correction, which means that indeed this can get to 0. And we computed the value of L lambda Young-Mills for which the Cj gets equal to 0, and we found that L lambda Young-Mills at which this happens is 0.92.
You remember more or less what is the value of G critical corresponding to this?
I'm sorry, I don't remember it. It's not so small actually, but if you consider instead G squared over 16 pi squared, which is the perturbative parameter that you should use, this is very small, but I don't remember.
Like very, very small, like 0.1 or 0.001?
I'm sorry, I don't remember. I can tell you later because I have it, but
and you know,
I remember that it's like because it depends on, while L lambda Young-Mills does not depend on NC, the value of G squared depends on NC. Okay, it's like 22 over NC, something like that. So maybe we can after 16 pi squared, I don't know.
And do you know if how stable is this? How robust is this result against higher loops?
No, actually, we don't know it. So this is something that could be explored. It's already quite complicated to perform computations at leading order. Maybe exploiting the fact that we have this BCFT argument, at least for the first computation, we can try to go beyond one loop, but I don't know if it's possible. Mm-hmm. Just with a quick computation, it may be wrong. I think it's more like 0.1 than 0.01 because it's 22 over. Yes, 0.1. So not so small. Okay, but. So what we expect is that we start from L lambda Young-Mills very small, and then we increase the values of L lambda Young-Mills. The first thing that should happen is the first scenario. So both the first and the third scenario seem plausible, but the first one looks the one which is more appealing because it's the first thing that happens when we start from small radius. Let me also say that the fact that we found an anomalous dimension which is positive for the lightest single scalar operator with no boundary condition is a nice fact, because this means that the merging annihilation scenario seems not to be present for non-boundary conditions. So this means that in principle, one can imagine to start from non-boundary condition at very small radius and then increase it without anything to happen to this boundary condition. So what we expect, this is just pictorial, but what we expect is that we start at weak coupling with two boundary conditions, Neumann and Dirichlet. Then we turn on the gauge coupling. And at some point, the Dirichlet boundary condition merge annihilate with another boundary condition, while Neumann boundary condition can be interpolated up to flat space. One open question is who is the star? So what we tried is simply we tried to perform to see in which kind of theory we end up starting from the Dirichlet boundary condition G equal to 0 and performing a double trace deformation from that. We can compute the dimension of the theory which is reached with this double trace deformation, and this is below the unitarity bound. So we expect that if indeed we can compute, we can reach the Dirichlet boundary condition with a double trace deformation from another CFT, this has to occur after some value of cannot occur at G equal to 0. So this is why we didn't continue this line up to G equal to 0.
But can it occur in the perturbative regime, or is it necessarily non-perturbative?
This we don't know actually. One thing that can be explored, this is not something that we are currently doing, but it may be done, is that if we go to, so this is ADS 4, D equal to 3. If we go consider instead ADS 3 plus epsilon, so in D equal, okay, so if we consider D equal to 2, the Dirichlet boundary condition is already marginal as an operator, which is already marginal at G equal to 0. But at D equal 2 plus epsilon, this occurs, so we have an operator which has dimension epsilon larger than marginality. So in this case, maybe we can treat the merging perturbatively. I don't know if it was clear.
So you're saying in D, in 3 plus epsilon dimensions?
Yeah, so
you have an ansatz for this D star, or no?
We actually don't have an answer for the star, but we expect the merging to occur at G squared equal to order epsilon.
Yeah,
So
then you should have an ansatz.
Yeah, the problem is that we didn't find a plausible ansatz. So I didn't like my collaborator Riccardo started a discussion with Shota about this, but they didn't find some possible candidate for this D star in this 3 plus epsilon theory. So I don't know if this is something that can be done in practice. Okay, so who is the star remains another question. Of course, all of these are a bit are conjectures on what may happen, because we did just a perturbative computation.
But it's also just to say that I mean, at the same time, the fact that the anomalous dimension is this is a fact, and it does not depend on the existence of the star. It's just a fact. You compute it, and that's what you find. So a very plausible scenario is that you have this merging and annihilation, but it could be something else. I mean, we just don't know. Just to say that once you compute this, I think.
Yeah, it's true. This is at least at leading order when we are close to where we have a small radius. This is a fact.
I mean, the merger and annihilation scenario is just a possible interpretation.
Yeah, it's an interpretation indeed.
But this is a result.
It's a nice, appealing interpretation. Let's say when we found that the value was negative, we were very happy, because this is the.
The reason I was asking is because in QCD there is a similar study.
Yeah.
I'm sure you're familiar with. And also there is no candidate for
QCD star. Yes, I know.
The end of the component.
Yes.
Yeah, this is a nice story. This merging annihilation. The problem is that it's hard to find candidates for the other theory.
Okay, perhaps we can.
Yeah, I'm finishing. So here are some possible open questions for the problem. One is who is the star? Another one is the possibility to have when the Dirichlet stops to exist. Do we simply does it simply mean that we cannot go further with the radius of IHES, or maybe we have some flow to Neumann boundary condition? And if this is there is some transition from Dirichlet to Neumann, is this transition continuous or discontinuous? This is something that we didn't explore. We can try to address these problems by using conformal bootstrap. And another possible direction is to try to add matter to the game and to see what happens. And this is something that we are currently doing. And finally, this is something that Joao Benedone suggested me during my PhD defense. Okay, so we are our results suggest that non-boundary condition is the boundary condition that we should consider to then explore confinement in flat space, Yang-Mills theories in flat space in general. So one possible open question is what can we do with that? Can we compute something starting from IHES and going up to flat space? And so one possibility is to compute ratios of dimensions of operator with Neumann boundary condition and try to interpolate this result up to flat space. The problem is that to take the flat space limit, we need to compute many orders and then maybe try to resum the results that we get, while performing computation is already with Neumann boundary conditions is even harder because we don't have the propagator is more complicated. So this is something that would be nice, but it's still quite hard to do in practice. That's all. Thank you very much.
Thank you very much for this very nice talk. So we got many questions already, but if there is some urgent question, please.
So from, I guess, both modern and old perspective, but this confinement phase transition can be measured by the expectation values in Wilson line, right? Which is a spontaneous breaking of the center. So can you do something that accesses that?
Unfortunately, we cannot, because Wilson loop in IHES at a large radius, at a large distances, behave like perimeters and areas behave in the same way for large dimensions. So we cannot really distinguish. I don't know if I was clear.
I don't understand. I guess
if we take some very large distance, areas and perimeters scale in the same way with the chordal distance. And so this means that we cannot really understand the difference between area behavior and perimeter, area law and perimeter law.
But I guess so area law, perimeter law, I think that the way to distinguish it is that one of them, you can add a local counter term on the defect that sets it to a constant. Right? Like the perimeter law, the point is that it's not that it's a perimeter, but it's that you can add a local counter term of the Wilson line that tells you that the expectation value can be non-zero. Whereas when you have area law, no local modification of the line operator can set it to zero at all, which is why it's not spontaneous. So I would assume that the same thing is true in general, because this fact is some fact about whether expectation values are zero or not. The perimeter is like a red herring. Perimeter is not zero, because I can just remove the perimeter part. So I think there should be an ambiguous way to compute whether it's zero or not.
I don't know. I never tried to do the computation. To think about the problem. I read that this is a problem of IHES, the fact that this area and perimeter scaling is the same. I don't know if, as you're saying, this is not the real problem. The point is that if we find different expectation value equal to zero or different from zero, but I don't know actually.
Any other questions? Okay, so if not, let's thank Fabiana again. And so we resume at 12, right? Okay, so